And as we know, an N well being doped into the P substrate, and there will be a depletion layer surrounded. So there are capacitance, parasitic capacitance in between the N well and the P substrate. And because N well is being used as a resistor, so we just model this whole thing here as a circuit like this. This is the other terminal of the resistor. We call it Vout. And this is Vin. So every single resistor here is 1 R square, which is a constant, right? And this is a C square. Is C square a constant or not? Why is that? So all these resistors are R squares. So every single resistor has the same resistance. No matter what's the width of the resistor, of the N well resistor, it can be like this, can be something like this, doesn't matter, since we just divide it into several squares. So these two guys has the same resistor, same resistance. What about the cap? Does this one have the same capacitance as this one? Definitely not, because this is larger. Okay. Whenever, if you see an example in the homework assignment, the capacitance of the C square is given. The reason we do that is because we have divided the entire N well resistor into several squares. Even though this is a constant, this is not, but we just divide it into several C squares. And this is how we model it. And so we have to find out the time delay from here to here. And I got so many capacitors and resistors here, how to do the calculation. It's not simply 0.7 RC anymore, right? If we label this as A, this is as B, this is as C, and this is as VL, we can find TDA to be, so from here to here, what's the time delay? It's going to be 0.7 R square C square from so the way we calculate this is you just look at, since we want to calculate a cumulative time delay from here to here, so we want to find out the contribution to the time delay for each capacitor. So for this first capacitor, it is definitely 0.7 R square, so this resistor and this capacitor. From here to here, what's the time delay? It's going to call TDB. Because the contribution of the time delay from this capacitor has been calculated, so we just ignore it. And the time delay from here to here involves two resistors and one cap. So the time delay from here to here will be 0.72 R square C square. So this is the contribution of the time delay from here to here for this capacitor. It's not exactly the time delay from here to here. Just make sure you are not getting confused about that. That's just a single contribution of this capacitor to the overall time delay. And we just split all these single time delays into several parts. instead of doing this just once, right? This will simplify the calculation process. And what about the contribution to the time delay for this capacitor? Since we have calculated these two, we can ignore them for now. And it involves 3 resistors and 1 capacitor. So that will be 0.73 R squared and times C squared, which is the capacitance of this capacitor. So TDC equals to 0.73 R squared times C squared So you can imagine if there are more resistors involved, you can just keep doing this. So what about TD out for the very last one here? For example, we have L numbers of resistors. So this equals to 0.7 times L instead of 1, 2, 3, but L R squared C squared. So if you want to find out the overall time delay from V into V out, which is overall TD, that equals to TDA plus TDB plus TDC plus TD out, which is 0.7, 1 plus 2 plus 3 plus L times R squared C squared. Right? And what is the summation of this term? L times 1 plus L over 2. I will learn this somewhere. That's a conclusion. So for 1 plus 2 plus 3 until L equals to L times 1 plus L over 2. R squared times C squared. And these two parameters are normally given for the calculation. And R squared is a sheet resistance, right? It's a constant. So when L is large, let's just say is large, we can ignore 1 plus L. We can ignore the 1 here. Just write it as 0.7 times L squared over 2, because L times L. So 1R is large, normally like 10 or larger. So 11 is pretty close to 10 in that case. If L is just 2, then 3 is not that different. Is not that different compared to, no, 3 is significantly different compared to 1, right? But when L is large, you can just write this as L squared and over 2 times R squared C squared. So 0.7 divided by 2, which is 0.35 L squared RC. That's a conclusion. Okay. So here's an example. 250 kilo ohms N-well resistor. And it is a 10 by 50. So the width is 10, width is 10, that's N-well. And length is 500 lambda, right? Assume the capacitance of a 10 by 10 square of an N-well is 5 femtofarad. Estimate time delay from B in to B out. So this is a 250 kilo ohms resistor, and the width is 10, length is 500. How many squares are there? This is 10, this is 500. So 50 over 10 squares. 500 over 10 squares, which is 50 squares. So L here is 50. So we got L already. And R is given. So what is C square? Ten by 10 is 5 femtofarad, right? So every C square is femtofarad. So TD equals to 0.35 times 50 square times the sheet resistance, which is how much? What's the sheet resistance? I have to say sheet is the most uncomfortable word to pronounce as a normal word in English. You have to be able to pronounce in an American accent to not misleading people. There are so many other words doing the same thing, but you have to, it's weird, like when you're pronouncing some of the names for the southern states, you have to pronounce it in the southern accent to sound like native, right? Like Texas, how to pronounce Texas? Texas, something like that. I don't know, Texas. Alabama. If you just write down Alabama, like a Chinese person to pronounce it, they will definitely pronounce it as Alabama, right? You have to pronounce it as Alabama to make it sound right. Louisiana, anything else similar. And Arkansas, they have to ignore S. Arkansas, why it's not Arkansas? Can I understand? All right, what's the sheet resistance over here? What's the overall resistance? Because this has to be the sheet resistance. It's R squared, right? So 250 kilo ohms for the overall resistance. And there are 50 squares. So it's going to be 250 kilo over 50 squares times C square. What is C square? 5 femtofarad. So this equals to 0.35 times 2500 times 5 K times 5 femtofarad, right? This is the calculation. And femto is 10 to the negative 15. Okay, it's not hard to do the calculation. Now let's look at the layers, the details of the layers of C5 technology. Since we have learned, there are poly layers, there are metal layers, but we need to know more details about it. You can find all the details in the textbook from Dr. Baker's CMOS book. And that's a substrate. On the top of it, there's a layer called Fox. And there are openings for the Fox where you can dope all these P pluses and N plus over there. So normally when I draw a transistor, I just ignore all these Fox layers, but they do exist. Another one here. It's another P plus, and they're being doped in the N well. And here's a gate. And there's the oxide layer, which is called gate oxide. It's a different oxide material. And that's the insulation layer, or insulator. And right above it, this is also the insulator. And it has all these metal layers in there. For example, this is metal 1. And these are the vias, goes to metal 1. This is via 1, the first via layer. Same here. This is also metal 1. All right. So I have draw all the layers without having any transistors doped in the P sub. These are all the layers available for the C5 technology. So that's Fox. That's poly. Insulator, but has the poly layers in there. With poly, silicon in that layer. And then there's another insulation layer which has metal 1 and another insulator has metal 2 in there, and then insulator but metal 3. So that's the insulator. So metal 3 is just a part of it, right? It's being submerged in that insulator. And there's another layer in C5 in the C5 technology called overglass opening. Which opens up the window on the very top layer, which is metal 3. So the color of the metal 3 in electric VLSI is yellow. The yellow color traces you can use if you do not have enough space to run the traces. And there's a overglass can be used for the metal 3 layer, which can open a window on the top of the metal 3. It's normally used as the pad. So you can have a bonding wire, can solder a very thin wire into the pad and connect this to the outside world. Normally it can be a way bigger pad or the pin of the IC chips. So you can connect this one to the probe to receive signals or inject signals into the chip, to the circuit, right? Because the metal 3 is eventually connected to the gates, to the active layers, all these N plus and P pluses, to anywhere. But all these layers are all the available layers in the C5 technology. You don't have any more other layers. So if you see an example or problem in the homework assignment, ask you to draw the cross-sectional view of the top view, you need to draw all these other layers as well, because they exist in the real world chip. I'm going to give you an example right now. So for example, if you see something like this in a quiz or in the homework assignment or in the exam, I just draw this on the paper. So these are the two traces, and here's a via. And I'm going to tell you this is metal 1, this is metal 2, and this is via 1. Doesn't have to be via 1, it just depends on how you name it. And I'm going to draw a line, a dashed line here, and I ask you to draw the cross-sectional view of this device on the paper. So that's the layout view from the top. And what you want to do is you have to draw it in scale, right? So that's a feature of the chip. The substrate can be in a variety of sizes or shapes, but I have to draw the cross-sectional view exactly as whatever is being offered, being provided here. Because this is metal 1, this is metal 2, so whenever there's no N plus P plus, so there are no transistors, just two metal traces. So don't want to ignore the Fox layer as the first oxide layer. And then on the top of it is a polysilicon insulator layer. That's a polysilicon, which has all the gates layer in there. This is an insulator. And then you have metal 1's layer in this insulator. And then metal 2. So I want to draw the metal 1, whatever metal 1 here, and metal 2 here, right? So the dashed line is being drawn here across this via. So definitely from the cross-sectional view, you're going to see the via as well. That's the length of the metal 1 layer. So here you want to draw a metal 1 trace first. That's the metal 1, the cross-sectional view. And because this is a via, and it's going to drill a hole to here, to metal 2, and that's the width of the metal 2 trace, and that's the width of the via, right? So just draw the via, and then metal 2. That's a solution for this problem. If the dashed line is being assigned or being drawn here, then you are not going to see any vias from the cross-sectional view, right? Just imagine you just cut from here. This is not on the top of the via, so you're not going to see any vias. And there are some design rules for the layout, because definitely you cannot just do whatever you want in the layout, because fabrication process cannot do anything you like, especially for this 500 nanometer technology. So the layout tool, which is the electrical VLSI you're using, we set up the design scale to be 300 nanometer. So all the scales, all the numbers are going to times that scale, which will be the real physical dimension, which can prevent you from using any numbers or any dimensions smaller than 300 nanometer. So it's always like one times at least. So it's a 1 time or 2 times, 3 times, 4 times the scale, times 300 nanometers. some of the rules I'm going to show you here, you are not going to use it. You don't have to consider this when you are designing the layout in electrical VLSI because it's always reporting errors. Whenever you put the two parts too close to each other, it's going to report errors and it cannot parse ERC. So not do that. So the CAD tools really help you to design the layout properly. So let me draw some of the design rules here really quick. So now what are they? This is metal 1. This is metal 1. That's a via. And that's metal 2. That's also metal 2. The minimum width for metal 1 is 1.5 times 300 nanometers. 1.5 the scale. And the distance between the two metal traces is also 1.5. And the minimum distance between the metal 2 layers is 1.5 times 300 nanometers. And the via has the exact size. Which is 1.5. And also the overlap of a via with metal 1 and metal 2 is 0.5. I'm not going to write it down here since you're never going to use this at all. You just need to know there are design rules. You cannot do whatever you want, right? So the electric VLSI is going to help you for the design. Two metals. This is metal 2. This is metal 1. And you know there must be a via in the middle to drill a hole and make the connection. So the via, you can consider the via as a resistor. It's not grounded. So M1, M2. So here's M1 and has a resistor. Drill a hole. The via is like a resistor and make the connection to M1. So what I want to show you here is all the design tools for the layout, they normally do not use a huge via for the fabrication. Instead, they use multiple smaller vias and they do not change the size of each via at all. Probably have seen this in the past in the layout. Still remember that? So in that case, and you can model these 4 vias as 4 resistors. This is M1, this is M2. What's the benefit of using 4 vias instead of 1 via? Because whenever you change the size of the metal and you want to make the connection from metal 1 to metal 2, electric VLSI can directly generate a via array for you. So you don't have to, you are not actually doing this by yourself. Automatically generating all the vias for you. Have you ever seen this? You probably just never thought about why it's doing this for you. So there are several benefits of doing this, right? The first, lower the resistance overall. Lower the overall resistance. Second, can lower the current for each via. Third, you got some backup vias. All the resistors in parallel, they are performing as a current divider. So the current used to flow through one via here can be divided into 4 components. So it lowers the current for each via. The reason is, I think the current rating for the vias is a constant. You cannot change it because it depends on the material. So if it runs a huge current through that via, can potentially damage the via. So you can imagine how many vias you have on each chip, probably thousands or millions of vias in there. If just one via is not working properly, then the chip is, is done, right? It's not working anymore. So it's better to have multiple vias so you can reduce the amount of current flows through every single resistor, every via. And even one of the vias is broken, you still have all the other vias is conducting metal 1 to metal 2. It still makes the connection from these 2 metal layers. So it's mandatory. Whenever you are having a large area, you definitely will have a via array instead of one big via, which can definitely improve the yield for the chip. Yield, Y-I-E-L-D, is a critical parameter for IC fabrication. Everyone can, not everyone, but there are so many players in the semiconductor industry can fabricate 7 nanometer chips. I think TSMC has been using that 7 nanometer technology for a while, for multiple years. And yesterday I saw a news saying Intel is going to invest $20 billion to start a semiconductor manufacture plant, Arizona or somewhere, to start their 7 nanometer business. It's like five years lagging compared to TSMC. And yesterday I just saw Intel stock just jumped to, increased by, I think, somewhere around 5-6% in one day. So why is that? Why? I mean, I'm pretty sure Intel can fabricate 7 nanometer nodes a long time ago. But the reason it's not being commercialized or it's not available in the market is because the yield is low. They are able to fabricate all these 7 nanometer chips on the wafer. This is a one wafer. Probably only 50% of the chips on the wafer is working, so which means they are functioning. So the yield is low. But TSMC probably can has 70% of the chips on each wafer to be functioning. So the yield is a critical parameter in the semiconductor industry. So there are so many ways can improve the yield. Have a via array is one of them. Now let's look at the active and poly layers. The active layer opens up the Fox or opens a window on the Fox layer. So initially, a P substrate, which is a wafer, has a Fox layer on the top. But the active layer is able to open up a window for the Fox layer So you can see the active layer from the electric VLSI library. You can directly grab it and size it in different dimensions. So what this does is, for the active layer, which is this shaded area, it's going to define the area to dope that N plus or P plus into the P substrate. But there's another outlying layer outside of the, which is larger than the active layer, which is called P select or N select, depends on the material. Let's just call it P select. You probably have seen this in electrical VLSI, or if you haven't, in the future, if you see that, you know what this means, right? So this is P select, which is the outside layer, and the inner layer is called P active, or P act for short. Right? P select is always larger than P act, same as N select and N act. N select is larger than N act as well. The dimension of the P act defines the dimension of the window on the Fox layer, the Fox layer, and it's going to dope whatever. You know, if you want to dope N plus or P plus, it will be able to do that. For example, this is N plus or a P plus for this case. The reason you have a P select layer, which is a little bit larger than the active layer, is because it's easier for alignment. You know, because all these dimensions are in micrometer level or sometimes in nanometer level. You can imagine if you want to exactly dope something here, and you don't want to have that window exactly the same size as this window. You want to make it a little bit larger. But these Fox layers are resistant to the dopant. So it's doping to this area, but actually it's fine because it's blocking those dopants from getting to the P substrate. And after the doping process, you can remove the Fox layer afterwards. Okay, but you don't want to remove it on the first hand because it's going to open up a larger window for the P substrate, and which can allow the dopants get into the P substrate. And the N-well layer is even a little bit larger than this. N-well. So the N-well is being doped into the substrate before you get a Fox layer and dope the P plus material in there. Because you want the P plus into the N-well. So it's not shorting the P plus material to the P substrate. That's a P-type P sub, right? Which is grounded normally. Okay, so that's a P plus node. Has a P act, P select, and N-well. Okay. So the P select is larger than active area, and N select is larger than N active area. The purpose of that is to minimize the issues of misalignment. It's still not very clear about how to align all these masks and dope the materials to the P sub. But I can give you some examples for the photolithography we have been doing in my lab, which is just for different devices. They are called MEMS, microelectrical mechanical devices, or as is just plural, it's just microelectrical mechanical devices. This is a research field which is used to be very popular, and still popular right now. If you want to pursue a graduate school, I think a lot of people in the mechanical engineering department and in the electrical and computer engineering departments have professors and research groups are designing MEMS in the clean room. So Dr. Jeff Jessing is one of the researchers used to work in the clean room all the time, about 8 hours a day in Sandia labs. And so what these people do is actually they just stay in the clean room 8 hours a day, 5 days a week, all the time, trying to get some results, you know. So they have wafers, they have all different kinds of substrates. And the first step is to deposit, can be a metal material, can be any other materials on a wafer, and then apply the material called photoresist, spin coat it on the top of that layer, the active layer you want to use, and apply a mask, and then UV expose it, and then etch out the photoresist, and then apply etchant to etch the metal layer. Eventually, you can get the feature you desire to be on the top of the wafer. And just have to do this for tons of times, so you can create a very complicated layer of different materials. Depends on how you design the mask. So this is a MEMS device under the microscope. I think this is in micrometer level, sometimes in the nanometer level. And all these materials are, you can see all these micro level springs on the 4 edges of this material. So what is this? Just think. Yeah, accelerometer, gyroscope. So all these features, all these micro level springs can sense the motion, inertia motion. So it's called IMU, inertia motion unit. The MPU 6050 you used in the microcontroller class is very similar to something like this. And because the motion can change the position of the springs, which changes the capacitance of the sensor, and it is able to sense that capacitance change and translate it into analog voltage, and then digitize it. So you can get a signal for acceleration and angular velocity in different directions. And I think this is another unit with different shapes of springs at 4 corners. It's another one. You know, even though it is a clean room, but you can still see there's something undesired object on the top of the wafer. You know, this is just a very complicated device. There are probably more than 5 layers of features. So let's draw let me just show you the process of how do we do it. For the photolithography we did in the lab, very simple ones. We use AutoCAD to draw it. The first MEMS device I developed in my graduate school is I used electrical VLSI to draw it, but eventually I found out it's not really convenient, because the electrical VLSI has all these shapes already being designed for as transistors and circuits, but not necessarily as some arbitrary shapes. So I think AutoCAD is way better when you're designing MEMS devices. For example, got a wafer. So Nick is a guru on this. He has done a lot of photolithography on that. So here's a wafer, for example. And let's look at the goal. So what's the final goal? So the final goal is I need a wafer has a little metal piece on the top of the wafer at this specific location. That's a goal, okay? You may have different shapes of traces, metal traces or features, and different layers, but we are just looking at the very bottom layer, which has a metal one, as a metal trace or metal dot or something on a wafer. So how to do that? The first first step, you have to deposit a uniform metal layer. There are several ways to do it. You can do a spouter coating. You can do you can use an evaporator to evaporate that metal material, so it's going to deposit on top of the wafer homogeneously. It's very thin layer in the nanometer level. And then you spin coat a photosensitive layer, which is called photoresist. So this material, there are two types of photoresists. One is called positive photoresist, another one is negative photoresist. So that depends on if it's being exposed to UV, are you able to remove it or strip it using a certain chemical or not? So for example, for a negative, this is negative photoresist. Then I need a mask, so you can design the mask. So now it comes to the mask, right? So you can design the CAD, design the shape or the feature in AutoCAD. For example, you can draw a line to make it transparent only at here, but all the other areas of the mask. So the mask is just a simple sheet, can be a plastic sheet, can be something printed on a glass plate as well. So I think for the semiconductor industry, they use glass plates instead of the plastic sheets we use. So that's a photo mask. Where allows you to design all the shapes you want to finally being left on the top of the wafer. So now I leave the opening because all the other areas are being covered by inks. So because you printed out that sheet, this part is transparent. And then you expose UV light from the top. So this little area here being exposed by UV as a negative photoresist, the material here, because this is a photosensitive material, will be cross-linked. Will make it resistant to a certain chemical we're going to use after this step. So after this, because this is just a mask, we apply it on the top. We just placed it on the top. We can definitely manually remove it. And after we remove the mask, it becomes something like this. We still have the metal layer at the bottom. We still have the photoresist on the top. However, the property of this area has been changed because it's being exposed to the UV light. And now I submerge this whole thing into a liquid. It's called developer, which will remove all the rest of the photoresist, but only leave this part on the top. Still the metal, however, only this part will be left on the top, and the material of this guy is a photoresist, cross-linked photoresist. Because this is metal, and then I submerge everything here in acidic solution or etchant, which can remove all the metals except for the material, the metal underneath this photoresist, because it's being protected by this photoresist. So the next step, only the metal, the piece of metal, and the photoresist on the top will be left on the wafer. The reason is this photoresist is covering this piece of metal, so it's protecting this without being from being etched by the etchant. And then there's a material called stripper. We can strip that photoresist off from the wafer, and eventually you only have a wafer and a metal piece, exactly thickness, exact with the exact thickness and exact location on the wafer. So you can see here's the goal, here's the final result, right? And if you want to deposit different layers, multiple layers on the top, so starting from here, so after you get the first product from the first experiment, what you want to do is you want to spin coat another uniform photoresist layer on the top. Do it first. Let's don't do this first. For example, for the second step, I don't want to do this. So starting from here, what I want to do is I want to deposit another metal layer just in the middle, on the top of the first metal layer. I'm going to do the second time of it. How to do it? So starting from here, so that's the final goal, right? And this is in micron level. How do you accurately just place this little dot on in the middle of this metal, but on the top? So first, you need a liner, which is normally over $300,000 for the ones used in the research labs in the university, because you want to have a mask that exactly has that opening in the middle and on the top of this metal piece, right? Have to align it over there. So starting from here to here, first you have to deposit a metal layer, a uniform metal layer, which definitely will cover up this guy, right? And then you have you want to apply a photo mask. Only leave a little opening here, and expose UV. So this little thing will be cross-linked. Here will be cross-linked. And then remove the rest of the photoresist, and then remove the rest of the metal, so you can have only a little metal dot on the top, sitting on the top of this first metal layer. And just keep doing this so you can eventually get all these multiple layers of the IC chip. That's how they design, how they apply all the different layers from the bottom to the top. So this is called a bottom-top fabrication process. From the bottom to the top, it's called bottom up. Actually, it's a bottom up method. All right. And introduce more details about just one little thing about the poly layer. I'm going to cover on Friday, and we'll give you the quiz. And also the models for digital design will be covered as well. And we'll keep working on the models in next 2 weeks, I guess. Okay. All right, don't forget the homework is due Friday, and we're going to have a quiz on Friday as well. All right, see you on Friday. Silicon oxide, right? Not silicon. Yeah, they have so it should be a chemical deposition tool, evaporator. They evaporate it, so you can design, they can deposit a uniform insulator layer.